Hey, let's finish up with notes from 9.8 power series. So example 3, find the Taylor series for f of x equals e to the 5x centered at c equals 2. Give the first four non-zero terms and the general term. Now we can modify existing Maclaurin series only when centered at c equals 0. So we're going to use Taylor series to generate these derivatives, and we're going to go through and find all the way up to the third derivative. So if e to the 5x is the original function, then the derivative is simply going through chain rule e to the u times u prime, so on and so forth. And we can then evaluate each of these functions and derivatives at x equals 2. So we get e to the 10, 25 e to the 10, and 125 e to the 10. So the first four non-zero terms, we have the first term here, plus, remember the first two terms is simply just writing tangent line equations. So our derivative is 5e to the 10 times x minus 2. And now we can follow the pattern, which is the second second derivative evaluated at 2, which is 5 squared e to the 10, over 2 factorial times x minus the center to this, the second power. And then the function, the third derivative evaluated at 2, which is 125 e to the 10 over 3 factorial times x minus the center raised to the third power. And the general term would simply be, we see this is 5 to the first, 5 to the second, 5 to the third. So therefore, our rule of sequence would be 5 to the n. E to the 10, notice that it stays constant and static the whole way through. And the n factorial, we see it's 1, 2 factorial, 3 factorial. And then the pattern for the exponent is also to the n. Okay, so we have to recognize the pattern to write the nth term. So the suggestion is that rather than writing 5, 25, and 125, we write it as 5, 5 squared, 5 cubed to help us locate the pattern a little bit easier, which will help us write our general term or general rule of sequence. All right, there are three special Maclaurin series we must know. They are e to the x, sine of x, and cosine of x. And these Maclaurin series are going to, or these series are going to converge for all of x. So the radius is infinity. Okay, come back to some of that here. Example 4. Here we have our function given by this power series. Find f prime of x and find f prime of 0. Okay, so f prime of x, we're going to take each term and find the derivative. So 1 becomes 0, x becomes 1, x squared over 2 factorial becomes 2x over 2 factorial. Okay, 3x squared over 3 factorial. And if we clean this up, we're going to get 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And so our derivative function is simply going to be e to the x, right? And because this does represent the power series for e to the x once we find the derivative. So f prime is going to be e to the x. F prime of 0 is simply e to the 0, which is 1. So f prime of 0 is just going to be 1 plus 0 plus 0 plus 0, which is still going to be 1. And as we see here, that even though we started with this function, after we find the derivative, we still ended up with the same function. And that matches with what we know about e to the x, because the derivative for e to the x is just going to be itself. And we see that pattern show true to form even in our power series and finding derivatives there. Okay, example 5. 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Now this is the same as e to the x. So if the derivative matches e to the x, then the integral should also match as well, right? If the derivative e to the x is e to the x, the integral of e to the x is also e to the x. So we're just looking at some properties of e to the x to kind of show that the derivative and that derivative are going to match up. So if we find the integral of 1 plus x squared 2 factorial, we're going to 1 becomes x becomes x squared over 2, x cubed becomes x to the 4th over 4, and that becomes 4 factorial. So on and so forth, plus dot 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 plus c. All right. And c is a constant, and we usually put the constant in the front in this case because we have increasing. We see the degrees are increasing by a power of 1. So if we move the c out in front, that will make the pattern match a little bit better. Now, this is essentially going to turn out to be the exact same as this. Now, they tell us that f of 0 is 1, so we can actually solve for c and show that c is going to be equal to 1. Because if I replace every x with 0, and replace f of x with 1, I can then see that c is also going to be equal to 1. And the antiderivative of this function is going to end up as the same, which matches with the property that we know with e to the x. All right, example 6, derive a Maclaurin series for sine of x, then take its derivative to derive a Maclaurin series for cosine of x. Now be sure to include the general term. You may have to adjust index for cosine to make it a little cleaner or to make it a little bit prettier or simpler. So here's the sine of x Maclaurin series, x minus x cubed over 3 factorial plus x fifth over 5 factorial minus x seventh over 7 factorial. And the rule of sequence is negative 1 over n times x to the 2n plus 1 over 2n plus 1 factorial. And the reason why the exponent looks like this is because we have to always guarantee an exponent of an odd number, which we see with the sine power series. Let's find the derivative. Now, let's see. What do we know about the derivative for sine? We know the derivative for sine is cosine. So let's see what the derivative of this is. All right. So the derivative of sine is cosine, so therefore the derivative of this power series will have to be the cosine power series. So x becomes 1, x cubed becomes 3x squared, and the 3 will cancel out with the denominator, forcing that denominator to be just 2 factorial. So x to the 5th becomes 5x to the 4th, and the 5s will cancel out with this denominator, leaving us with just 4 factorial. So once we know, if we memorize the series for sine of x, we can always derive the cosine by simply taking the derivative of the sine, in case we forget what the cosine's power series is. Now here, if we find the derivative for this 2n or 2n minus 1, we can clean this up to eventually make it look like x to the 2n over 2n factorial with the alternator in front, negative 1 to the n. And this makes sense with the exponents because we expect the exponents to be positive with the cosine exponents. All right, last page, last few examples here. Once we have these series memorized, and perhaps those for 1 over 1 minus x, which we're going to get to, we can conveniently manipulate them to suit other transcendental functions. We can manipulate these 3 special series to find other series by using the following techniques. Note the radius convergence may change, however. We substitute into a series for x. We multiply or divide the series by constant. We can add or subtract 2 series. We can differentiate or integrate a series. This may change the interval, but not the radius convergence. And then we may recognize the series as the sum of a geometric power series. Okay, important, we cannot change the center on an existing Maclaurin series. It stays at c equals 0. Okay, example 7. Find the Maclaurin series for f of x equals sine of x squared. Let's see. Let's write the power series for sine of x. Now all we do is we can just replace all the x's with c with all the x's we see with x squared, and once we do that we get x squared, x to the 6th, x to the 10th, and we also want to make the adjustment to the general term, So the n gets replaced, the x gets replaced with x squared. And if we clean this up, we get negative 1 to the n, x to the 4n plus 2 over 2n plus 1 factorial. Find a Maclaurin series for x cosine of x. Well, to do that, we're going to build this function by first creating the power series for cosine of x. And then next, we're going to just multiply each term by x to create the x cosine of x. Distribute the x through, basically. So x minus x cubed plus x to the fifth minus x to the seventh. So I'm just adding another x, so I'll just make it x, so 2n plus 1 to update the general term to make it match to be the general term for x cosine of x. Okay, final example here. Find a Maclaurin series for e to the x plus e to the negative x over 2. We're going to construct the series one portion at a time. We're going to deal with e to the x first. So here's e to the x. E to the negative x, which is the second portion, we're going to just replace every x we see with a negative 1. And so that's just going to alternate the signs for each for the terms. So I'm just going to basically turn that include a negative 1 to the n in front. Now if we add these together, then that will give me the e to the x plus e to the negative x. So 1 plus 1 is 2. The x's will cancel out. These will combine to double to be 2x squared over 2 factorial. The next terms will cancel out. And then the following term will be 2x to the fourth. We can see the pattern now, right? So the numerator will produce 2x to the 2n over 2n factorial. Okay, so we look at the pattern. We create our general rule of sequence. And finally, this is the same thing, divided by 2 is the same thing as multiplying by 1/2. So if I multiply through with a 1/2, then that's going to essentially cancel out with a 2 in the numerator, and I can just cancel out, cross out the 2 from the numerator to cancel to eliminate with the 2 in the denominator. And so here is my rule of sequence for this h of x. And the best way to do these types of problems is to break it up into small portions, start with what we know, then build e to the negative x, then build to the sum of the numerator, and then multiply or divide by the 2 in the denominator.